You know, for decades, we've thought of the moon as a destination, a place to visit, plant a flag, and then come right back home. But all of that is changing. We're on the brink of moving from just visiting our closest neighbor to actually living and working there. So let's jump right into this incredible next chapter for humanity. And that really is the big question, right? It's not about the quick sprint of an Apollo mission anymore. Now it's about the long game, the marathon of building a real sustainable presence there. And, well, the answer is a whole lot more complicated than you might imagine. Look, bigger rockets are great, and yeah, we absolutely need them, but they're just the delivery service. The real work, the real challenge, begins after they drop off the package. Exactly. The whole journey from a plan on paper to actual boot prints on a permanent lunar base is paved with thousands of these seemingly small technical hurdles. Everything from what kind of power plug to use to how the software talks to each other. And in space, those little problems become monumental challenges. So where do you even start with something this huge? Well, you start with the master plan. Just like building a skyscraper, you need a blueprint. And for the United States, that big picture plan is the National Cislunar Strategy. In this image, wow, it really shows you the new scale of what we're talking about. We're not just thinking about low Earth orbit anymore, where the International Space Station hangs out. This strategy officially lays out a whole new sphere of human activity, this entire region of space that's dominated by the gravity of the Earth and the Moon. And here's the official term for it, Cislunar space. It's not just the Moon itself. It includes lunar orbit and even these super stable spots in space called Lagrange points. This is the new arena, the new playground for science, for exploration, and for business. Okay, so we've got the blueprint, but think about it. You can't build a city without building codes, right? You need a power grid. You need rules so that everyone's stuff can work together. The exact same thing is true for the Moon, both for physical things like electricity and for the data that's going to be its lifeblood. This historical parallel is just fascinating. Back at the 1904 World's Fair, the Palace of Electricity was just a total mess of different plugs, different currents, a complete technological chaos. And the Open Lunar Foundation is warning that we're at risk of creating the exact same Babel Tower on the Moon if we don't agree on some standards right now. Seriously, just try to imagine that. A rover from one country can't share its data with a habitat built by a private company. A science experiment can't plug into a lander because the outlet is different. It would be an absolute logistical nightmare. We need a common power grid, and just as important, we need common digital roadways. Okay, so on the digital front, this is where it gets really, really cool. To build these digital roadways, we need modern data formats. So think of old formats like JSON. It's like getting a book. You have to read the whole thing, take your own notes, and then you can use the information. It's slow. But these new formats, like flat buffers, they're called zero copy. That means the system can read the data directly from the source. No rewriting, no extra steps. It is incredibly fast and efficient. Absolutely perfect for when you need things to happen in real time up there. And look, this isn't just some idea on a whiteboard. This is happening now. We're actively replacing formats that are decades old. Things like the TLE. That thing has been the standard for satellite data since the beginning of the space age. It's getting swapped out from modern, efficient, standardized systems. This is the digital foundation for a moon that lots of different people and countries can use together. All right, we've got our blueprint and our building codes. Now, the first truck has landed. And this brings us to what sounds like a simple problem, but it's actually a huge one. How do you get the cargo off the truck? Welcome to day one at the lunar construction site. This is the question. You've just landed a billion-dollar piece of equipment on the Moon. Great. Now, how do you get it off the lander? You can't just pack a giant construction crane, right? It's way too heavy. You need something clever, something lightweight, and something versatile. And the winning idea? Absolutely brilliant. It's called the Lightweight Inflatable Delivery System, or LIDS. Instead of heavy steel beams, get this, it uses an inflatable gantry. It packs down super small and light for the trip, then poof, it inflates into this big, stable structure. It's got a rotatable crane, so it basically acts like a super versatile forklift and a winch all in one. Just a really, really clever solution to a tough problem. So the equipment is on the ground. What's next? Well, you gotta learn how to use it. Down here on Earth, you can practice, you can make mistakes, no big deal. But on the Moon, there are no do-overs. So how in the world do you write the operator's manual and train the drivers for a place with 1/6 the gravity and that crazy, sharp, abrasive dust? You build the ultimate simulator. And I don't mean for fun. I'm talking about a physics-based simulation so accurate, it's basically a perfect digital twin of the real lunar environment. It's a place where engineers and astronauts can test things, train on them, and even break them in a virtual world where the stakes are zero. There's a whole science behind this. It's called terra mechanics. And it's not just about getting the gravity right. It's all about precisely simulating how a rover's wheels are going to sink or slip or get a grip in that superfine, powdery moon dust. You have to nail this physics, or you'll never know if a rover can actually get up a hill or dig a trench without getting hopelessly stuck. So here's the breakdown of how they do it. First, they build a perfect digital copy of the vehicle. Then, they model the terrain using real data from the moon, right down to the last grain of dust. Then they plug in all the weird physics, the low gravity, the lack of atmosphere, those crazy long dark shadows. And the final touch? They generate synthetic images that look exactly like what the rover's cameras are going to see. And that right there is the whole point. This virtual simulation isn't just for practice runs, it's a fundamental part of the design and testing process. It's how we de-risk these incredibly complex and expensive missions, ensuring that when our hardware finally gets to the moon, it works exactly the way we planned. So from a huge national strategy all the way down to the physics of a single grain of dust, you can see how we're laying the foundation for our future on the moon, piece by piece. But as we write these new rules, these digital standards, these operating procedures, we have to ask ourselves a big question. Are we building a closed system or an open platform for everybody? The moon is a blank slate, and the decisions we're making today are going to determine whether it becomes a world that benefits all of humanity. What kind of future are we going to choose to build?